So Dalton's law of partial pressure, the pressure total is just the sum of all the individual pieces. So when pressure A plus pressure B plus dot, 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 if there were 3 gases, you'd have 3 pieces. Okay? So if you're talking about atmospheric gases, the major substituent would be nitrogen, would be about 80%, is about 80% of the atmosphere. So 80% of the pressure in this room is coming from nitrogen's pressure. Okay? About 20% of the pressure in this room is coming from oxygen's pressure. The pressure of each individual gas is pretty much independent of the other gas. All the pieces just add together, and it doesn't matter what they're made of exactly how much. If it's 20% one gas, the 20% of the pressure will come from it. So putting some math or numbers to this, we have a sample of air consisting of oxygen and nitrogen. I'm ignoring the other tiny pieces to simplify this a bit. We're told the partial pressure of oxygen is 19.1. The partial pressure of nitrogen is 80.5. And we're asked what the total pressure is. And then I've got a bit of an illustration that I'll address on the very bottom. So our pressure total is going to be pressure of oxygen plus pressure of nitrogen. And we're just going to add them up. So oxygen was 19.1 kilopascals, nitrogen 80.5 kilopascals. My 2 pressures are the same units, so I don't have to do any conversion. So we're just going to add these up. No, we don't do a lot of addition in chemistry or science. We multiply. So you get rusty on the sig-fig rules for adding and subtracting. Okay? So it's a nice chance for me to recap them. You just track places, and you keep the lower amount of places. So our first number is to tenths. Our second number is to tenths, so it's a tie. So we're going to record our answer to tenths. Don't count sig-figs. Just track decimal places. Or places if there's no decimal. So I get 99.6 kilopascals. Visually, and you don't even have to put the bottom boxes in your notes. Okay. Oxygen is about 20%, so I'm going to use 10 little dots for my example. So if I do 10 dots, it's a total, about 2 of them or 2 of our molecules are going to be oxygen. So they're going to be bouncing around, and they're going to hit the container so often. That's where we get our pressure. And that's where the 19.1 kilopascals is coming from. And they're going to be pretty independent from our nitrogen, which is going to be about 8 of 10. So that's 8, and they're all bouncing around. They're going to hit the side of the container. The blue dots are going to create a pressure of about 80. And when you put them together, we have 2 blue dots, we have 2 red dots, 8 blue dots. And Dalton's law says you just add the pressures from both. Okay. These are point sources, there's gaps in between them. We're ignoring any forces between the gases. They're really independent of each other. And it's only gases that really act like this, independent of each other. So now you're not really going to get test questions on Dalton's law. It's going to be a building block skill. It's a pretty simple relationship. Okay. This would be more like what I might test you on, or you might see on an AP exam next year. We got a mixture of 2 gases forced into a container, and we're going to figure out the partial pressure of each. So a 10-liter glass jar, I'm going to draw that first. I'm going to put a nice lid on it. So this is 10.0 liters, and everything is going in there. Is filled with 20 liters of 1 atmosphere hydrogen and 20 liters of 1 atmosphere helium. And we're asked what's the partial pressure of each gas inside that 10-liter red container. So I've tried to take all of our information and kind of organize it visually. 20-liter container, and we're putting in a blue color-coded gas and a green one. So just a reminder of Boyle's relationship, P1 V1 equals P2 V2. And we can use this. We know the pressure before we do anything for hydrogen is 1 atmosphere and 20 liters. After we put it in the red container, which I'm going to call it my 2s, we want to know the pressure, and we know the volume is 10. So we can use, I'm going to rearrange this for P2, and that will be our partial pressure inside the container. And we'll do the exact same thing for hydrogen, and then we'll do the same calculation for helium if we need to. So for hydrogen, we can get its partial pressure, which is P2. And I'm going to rearrange this without showing my work. We end up with P1 V1 over V2, where 1 is original and 2 is inside the red container again. So our pressure 1 is 1 atmosphere. Our original volume is 20 liters. And our final volume is the red container. That's only 10 liters. With our gas laws, we got to watch our units, but we had liters and liters. And I didn't say what pressure units I have to use, so don't change them if I don't make you change the units. We're just going to leave it in atmospheres. So that's going to be 2 atmospheres. Okay. I would hope some of you maybe wouldn't even use an equation or wouldn't even use math or use, calculators. The volume was cut in half, so you know the pressure should double, even without using a formula or anything. Hopefully that makes some intuitive sense. So we're going to have 2 atmospheres of pressure inside this container. What about helium? Well, it's the same volume originally and the same pressure. So it's the exact same black math I already did. So the math, I'm not going to write it again. We would have the same calculations as below for helium, just because I made them symmetric or identical. So inside this container, we're going to end up with 2 atmospheres of helium and 2 atmospheres of hydrogen. Okay. So what is the partial pressure of each gas and the total? Partial pressure, so hydrogen is 2 atmospheres. Helium is also 2 atmospheres. Dalton's law tells us the pressure total I'm not even going to write out the formula. The pressure is just the total of all the pieces, 2 plus 2. Each gas is 2 atmospheres. The two of them together would be 4 atmospheres. So when you're doing partial pressure of each gas, you're going to use Boyle's law and solve for P2, the pressure, after it's been put into a container. And it can go either way. You can put a larger volume into a smaller, or a small volume into a bigger container, where it's going to expand and take the size of that larger container. Okay. So same thing again. We have a 125 ml sealed vial this time, and we've pumped in 505 mils of 108 kilopascals neon, a noble gas, and 251 of argon, another noble gas. So very different amounts of each, both larger than the container. And same question, what's the partial pressure of each? What's the total? So we'll have to use Dalton's law. And then just a reminder, I keep saying we talk about gases, and we're not really concerned about the type of gases in terms of using our gas laws. And that is Avogadro's law that I keep saying without the name. So Avogadro's law is just the total number of moles of any gas will have the same pressure. So a mole of neon or hydrogen or argon has the same effect. Okay, it's Avogadro who came up with that relationship. Okay. The only thing to highlight there is it says moles, not mass. Different masses of gases will have different pressures, but different moles, no, same pressure. We don't care what the gas is. So I'm going to draw my visual while you finish writing. So we have a smaller vial. We're going to put in neon. We're going to put in argon. They're both being compressed down to 125. So before we even do any math, we know for compressing the gases, volume down, pressure up. So the partial pressure of each of those gases should go up. We'll figure that out. Now, I'm not going to rearrange Boyle's law. I'm going to jump right to P2 equals. Pressure 2, which is inside the container, is pressure 1 of the gas before we compress it, volume of the gas before we compress it, divided by the volume of the red container. This V2 is the same for both gases because we're putting them into the same place. So I'll do this for neon, and then I'll do it on the far right for argon. So P1 so that'll be our calculation for neon. We have milliliters instead of liters in this question, but it doesn't matter. Both volumes are milliliters. They cancel out. No reason to convert to liters. So the final pressure, or P2 pressure for neon, is 436 0.32 something something. I've got more than enough sig figs written down. I need to keep at least 3. I've written an extra one down. That's fine. I'm not done with my answer. Argon. So its pressure, pressure 1 was 40.2 kilopascals. Its volume is 251 milliliters. It's also being forced into that 125 ml small vial. And its final pressure is 80.721 kilopascals. I didn't write out the 2-1 on the board. So what is the partial pressure of each? I'm not going to rewrite them this time. I probably should, or you should on a quiz. Most of the pressure is coming from neon. A smaller amount of the pressure is coming from argon. What's the total pressure? I just have to add those 2 up. I'm not going to bother rewriting them for the sake of time. And we have 3 sig figs in pretty much all of our data. So when I add them together and then I round, I get 517 kilopascals. I end up being limited to the ones place here when I do the addition, because this number should really only have 3 sig figs, so the ones place. This one would be the tenths. So between the ones place and the tenths place, I keep the ones place. Okay. So we've let partial pressures kind of go again. We're going to use that theme, but in a very different context. A reaction creates 25 grams of propane gas. So prop always means 3 carbons. So it's C3H8. The gas was collected in an inverted graduated cylinder in a water bath. What volume of propane was collected at 20 degrees Celsius and a pressure of 90.2 kilopascals. And I'll explain this diagram. It's a typical way that we can collect any gas, including the one in this question. So explaining the diagram, this would be a filled chemistry lab sink. You would flip an inverted graduated cylinder into the sink after you've filled it full of water. So before you've collected any gas, you're going to have this whole thing filled. And if there's no gas inside, you're not going to have any air bubbles or anything at the top. It's going to be totally full, and we're going to read our volume from the top. So that would be 0 volume of gas before we run our experiment. Okay. Now, you could either run a reaction in the water underneath the graduated cylinder, or run a reaction on your lab bench with a hose coming out of a sealed vial and force all the gas to go under the water, and then be buoyancy would bring it right up to the top of the blue that I filled in. Okay. We'll do it both ways. Some rate of reaction grade 12 labs will use this setup on the bench with an Erlenmeyer flask and hose pump our gas in. As the gas is formed, the water level is going to start dropping. Okay. So maybe this is our final volume. You could read whatever the volume is off your graduated cylinder. Now, once you get your volume formed, we've got to get rid of this height. If you can drop by adjusting your graduated cylinder up and down, get this red line down to the water level, then the pressure outside will be equal to the pressure inside. So I want that to be an I. That's only true when the water levels are equal to each other, so that there's no gravitational pull of water expanding the gas. Right now, this column of water would actually be expanding this gas. But once we get the water level equal, there's no water to pull the gas down. P outside is equal to P inside. I can measure the pressure outside super easy. The pressure inside, that's really difficult. Okay? Which is why we got to get the two water levels equal. Okay? Once you get the two water levels equal, we know the pressure outside is the same as pressure inside. Temperature, we could just measure the temperature of the water that is close to the gas. Okay? Volume, we can read off our graduated cylinder. We can get P, we can get V, we can get T. Okay? We can get pretty much anything we need to do some calculations with the ideal gas law. The only thing we have to realize is that the volume of gas that we have up here isn't just methane. It's a mixture. We got partial pressures. In this question, we're going to have C3H8, and we're going to have this water is going to have a vapor pressure. Okay? So we're going to have to remember that we have some water vapor up there also. Okay? If we want to know the amount of pressure or volume from methane, okay, we just have to know water's pressure, and we can subtract it off the total. This pressure plus that pressure is the total. Okay. How can we get the vapor pressure of water? Well, we've got it in a table. If you flip back in your notes, or I'm going back, okay, the vapor pressure of water is well documented at different temperatures. At 20 degrees Celsius, we would expect to have a little over 2 kilopascals of pressure coming from the water. Everything else is going to come from our gas. So we're going to need that purple box number for this calculation. Okay. So I already mentioned the ideal gas law, but you're thinking right now on what strategy should I use? Is this a before and an after? And no, there's no mention of V1s and V2s and P1s and P2s. So that's where the ideal gas law is our strategy. PV equals nRT is our strategy when there's no before and after. And this question is asking about volume. So this isn't Boyle. This isn't a combined gas law like we just did. So I'm going to run through the variables, and when we get to pressure, I'm going to have to take the water vapor pressure away from that 90.2. Because 80 some of it, high 80s of that is actually our propane, is our gas that we made. So moles, we need N, I'll do nRT, and then the P last. So moles, so we have propane, we have 25 grams of propane, mass over molar mass, 25.0 grams, divided by the mass of 3 C's and 8 H's. So you're using your data booklet, adding up all those individual atomic masses. I get a bit over 44. So that works out to 0.5669. Okay. I've written an extra digit. Okay. Okay. You could round that to 0.567 for the sake of your notebook, but you keep everything in your calculator. So that's moles times R, 8.314 kilopascals times liters divided by moles times Kelvin. which those units are a nice reminder just before we put in our temperature that we have to use Kelvin units. So 20.0 to go to Kelvin is the bigger, so we add 273.15. So I get 293.15. I didn't write out the last digits, kind of running out of room, but it's 293.15. Last, we've got our pressure. Now we want pressure not of the whole thing. So 90.2 kilopascals is the whole pressure, but I want to take away what's from water. So that's 2.34 kilopascals, looking it up in that table. So I've rounded that. You'd want to keep 87.86. So our pressure of just propane, 88.86. You've got a lot of calculation, lot in your calculator to try to pull down all those extra digits. I've rounded a little bit, okay, but you have to not do that to the very end. So I've got everything in now. Moles cancels moles, Kelvin and Kelvin, kilopascals and kilopascals. So I haven't made any unit errors. Liters did not cancel. So that's my units. And sig fig wise, we had the temperature ended up being to 1 decimal place. So we ended up with 4 sig figs with 1 decimal place after we went to Kelvin. I didn't show them all. Our pressure's 3, our mass was 3 sig figs. We end up keeping the lowest sig figs when we do all that multiplication and division is 3, so I rounded it to 15.7 liters. Okay. Okay. If you hadn't ignored the water, you would get a slightly higher volume. Okay. So the last bit of gases for AP part of Chem 20, partial pressure and molar ratios. I really want to explain this first before we do any math. The partial pressure of any one component we can get by taking the total pressure and multiplying by a ratio. And I want to kind of dive into this ratio and the meaning of it. Okay. We have to take the moles of that one component and divide it by the moles total. So that hopefully, when I see that, I'm kind of thinking of a percent, but it's not a percent. A percent is how much you have divided by the total times 100. This is just how many moles you have divided by the total, not times 100. So that in blue brackets isn't a percent. What would we call it? It's a D word version of a percent. It's a decimal of the percent, okay? But it's just, you know, so if the percent was 80, if something is 80% nitrogen, then that ratio would be 0.8. 0.8 out of every 1 mole would be nitrogen, okay? So we want to take our concept of a percent of a gas, and that's all this formula really is. The percent is turned into a decimal, and then the total pressure times the percent as a decimal is the pressure of that piece. Okay. Now the percents can't be done by mass. They have to be done by moles. That's kind of coming from Avogadro's law. Okay. Every ideal gas we can use, treat it as gas independent as long as we use moles. Okay. We can't use mass to do this. So we're given the mass of hydrogen and the mass of helium, and we need to figure out how many moles we have of each. So we can take the moles of one component, divide it by the moles total, really just get our, what is our percentage of hydrogen by mole? What is our percentage of helium by moles? And then we're good. Okay? Our total pressure is 88.2. Okay? If something is 75%, if this happened to be 75% hydrogen, would take 75% of that total and would have our answer. So let's start working on getting the moles of each component. We need the mole total, so we need the moles of each. And then we can do a molar ratio. So there's our hydrogen. I'm going to turn that into moles. That's mass over molar mass. So 2.56 grams divided by the molar mass of elemental hydrogen, which is not one of them. Hydrogen is one of your diatomics. So that is 2.02 grams per mole. Each hydrogen atom is a little over 1. So in total, I got 1.2733 moles. So I'm just going to put the 27 down on the board. We also have to know the moles of helium. So I'm going to do the exact same calculation, but for helium, moles is mass over molar mass again. Now helium, we have to think, is that diatomic? Does it come in pairs or ones? We need to know its spot on the table. Helium atomic number 2 is a noble gas. They don't react. They don't bond with anything. They all come in ones. So its molar mass is just 1 unit. So we have 1.35 grams divided by the mass of just 1 helium in our table, which is exactly 4 to 2 decimal places. So we have 0.3375 moles. I'm rounding it to 3 sig figs to put on my board, but again, you're going to keep them all in your notes. The same as the red, 1.2733, I just didn't write that down. Okay. So now we can do our molar ratio. The pressure of one component, so the pressure of hydrogen is the total pressure times the hydrogen moles divided by the total moles. So our partial pressure of hydrogen is pressure total times the moles of hydrogen divided by the moles total. Pressure of hydrogen is 88.2 kilopascals times, okay, now we're doing that decimal version of a percent. Moles of hydrogen, 1.2733 divided by the 2 moles added together. Let's see, so that's a little over 0.3 plus 0.27. So the 2 underlying green lines, I got 1.60482. I didn't write the 482, but I used it all in my calculations. Okay. So this is really a percent. We're not going to actually divide what's in green brackets and multiply by 100, but that would be the meaning. That is our percent of hydrogen in this reaction by moles. The moles cancel out. Okay. So the percent of that 88.2 works out to be 69.9796. So 69 point something. I want 3 sig figs, so 69.97. I'm going to round up to 70 because it was 69.2 697. So 70.0 kilopascals due to rounding up the 9 in the decimal up to 10 or 0. So we have 70 kilopascals of hydrogen. We could run all the math again, use this formula again for hydrogen, but there's really no point. There's only two pieces. 70 kilopascals plus whatever helium is has to be the 88.2. So instead of running partial pressure of helium, 88.2 times the molar ratio of helium, what are we missing? 70, we need another 18.2 kilopascals are missing to get up to the blue number. Pressure total, if I just use Dalton's law, it's the fastest way. Pressure of hydrogen, pressure total is the hydrogen plus the helium. Well, we know the total is 88.2. We just figured out that's 70. Instead of doing this whole calculation again, helium has to be the missing amount. And it works out 18.2 is how many kilopascals we're missing. Okay. So you don't have to run the formula again. You could put in helium's moles in here, rerun that, and you should get 18.2. So what's the question? What's the partial pressure of each? I didn't write my units in this little summary of Dalton's law, but that's our two partial pressures.